Today, I'm going to present our paper, Rotationally-Temporally Consistent Overview Synthesis of Human Performance Video. In this paper, we are tackling a new task of synthesizing an overview video of a human subject that is rotationally and temporally consistent. This task consists of following three subtasks. First, synthesizing an overview human video given videos taken from different viewpoints. Second, the synthesized video should be consistent across different adjacent angles. Third, the synthesized video should be consistent across consecutive time steps. We can first think of a straightforward method, which is to run an image-level method in a frame-by-frame manner. However, the results are greatly inconsistent and show flickering across different angles and time steps. Therefore, in overview video synthesis, it is important to consider the rotational and temporal consistency. We start from an image-level baseline inspired by recent 3D-aware view synthesis pipeline. In this baseline architecture, image from view K goes through a series of 2D and 3D convolutions to become a volumetric representation. This volumetric representation is then trilinearly resampled to the query view. This resampled representation then goes through the decoder to become a final 2D output. For our task, we propose the 3D gated volume completion. Also, we design a Siamese architecture with temporal feature sharing. Lastly, we propose a rotational and temporal consistency loss. More specifically, first, at a frame level, we propose a novel 3D attention module which efficiently and effectively enhances the volumetric representation. We propose to approximate the full 3D gating values by decomposing them into 2D gatings along canonical XYZ-X. This allows reducing memory without sacrificing performance. Decomposed 2D gating values are applied to the latent volumetric representation to differentiate the foreground voxel points from the background voxel points. Also, this gives more attention to the meaningful voxel points. This is different from the traditional 3D convolution, which treats every voxel point equally. Our gated volume completion therefore produces better volumetric representation. Second, our model takes two consecutive frames, and their features are shared and augmented between the Siamese towers. The key idea of this temporal feature augmentation is to leverage complementary information between t-1 and t. This approach allows us to improve the perforing quality since consecutive time steps may reveal more visible pixels of the same model. Also, temporal coherency is greatly improved since the generation of the final output is conditioned on both consecutive time steps. Specifically, given the features at the time step t-1 and t, our temporal augmentation module learns the flow warping to align the feature at t-1 onto the feature at t using off-the-shelf flow estimator FlowNet2. The warped feature is then element-wise summed with the current features to become an augmented feature. This augmented feature goes through the decoder to become a final synthesized image. This augmentation process is designed to be performed in a temporally bidirectional manner. That is, feature T is augmented conditioned on the feature t-1 and vice versa. Finally, we present a novel loss function that enforces rotational and temporal smoothness of the synthesis result. The rotational consistency loss is designed to let the network learn the consistency across the different adjacent angles. Optical flow is calculated between the two adjacent ground truth images at the query angle Q and the adjacent angle L. Then, in the warping layer, this flow is used to warp the pixels of the synthesized image at the query angle Q to the adjacent angle L. This warp image is then compared with the synthesized image at the angle L to calculate the rotational consistency loss, and this loss in turn infers smoothness between the adjacent synthesized views. The temporal consistency loss is also calculated in the similar manner between time step t-1 and t. For the detailed explanation, please see our paper. To facilitate the training, we collected synthetic human performance dataset, including diverse appearance and action sequence. We compared with the volumetric representation-based method on our MVHA dataset with 3 testing scenarios, which are scene models with unseen poses, unseen models with seen poses, unseen models with unseen poses during training. Our method outperforms on all scenarios. We also experiment on other human dataset, PVHM. Our method outperforms other methods on both MSE loss and SIM score. We experiment on rigid object dataset as well, which is ShapeNet. Our method outperforms state-of-art methods in both the car and chair categories. This is the result on our MVHA dataset with SIM model and unseen pose during training. Compared to per-frame-based method, our method is able to reconstruct fine-grained details, such as arms and legs, more consistently across different angles and time steps. Our method generalized well to the unseen models and unseen poses during training as well. We also observed consistent improvements with other human dataset, PVHM, and on rigid object dataset, the ShapeNet car and chair categories. Our contributions to human overview video synthesis can be summarized as follows. First, gated volume completion. Second, Siamese network with temporal feature sharing. Third, rotational and temporal consistency loss. Fourth, MVHA dataset. To see more of our explorations on this human overview video synthesis, please see our full video and slides. Thank you.